Good evening, and welcome back to the Late Lab. Settle in wherever tonight has found you. Maybe you're already under the covers, maybe you're listening from a dimly lit room, or perhaps this is simply something quiet to keep you company at the end of a long day. And before we disappear too far into the strange little corners of physics, tell me where in the world you're listening from tonight. I always enjoy seeing just how far these late-night experiments in curiosity manage to travel. If you've been enjoying these slower journeys through science, you can help the Late Lab along with a like and a subscription. And if you're already part of this growing collection of sleepy scientists, thank you for continuing to spend your evenings here. It really is appreciated. Tonight, we're stepping into one of the most awkward questions in modern physics. Quantum mechanics is astonishingly good at telling us what we are likely to observe. Its predictions have survived experiment after experiment with almost ridiculous precision. But hidden inside all of that success is a problem physicists have been arguing about for nearly a century. Before a measurement, quantum theory can describe several possible outcomes at once. After the measurement, we see only one. And somewhere between those two statements sits the quantum measurement problem. So, get comfortable. No laboratory coat required, no advanced mathematics expected, and thankfully no need to place an actual cat inside a box. Let's wander into one of physics' most successful theories, and ask why nobody can quite agree on what happens when the universe finally has to choose an answer. Quantum mechanics has earned an unusual place in the history of science. It is one of the strangest theories ever developed, yet also one of the most successful. Its predictions have been tested again and again, across scales ranging from individual particles to some of the most sophisticated technologies ever built. And the results have been remarkably consistent. The colours of atomic spectra, the behaviour of electrons inside solids, the operation of semiconductor electronics, the light produced by lasers, and the precise transitions used in atomic clocks all depend on quantum principles. Modern medical imaging techniques rely on carefully controlled quantum properties of atomic nuclei. Quantum mechanics also sits beneath much of modern chemistry, explaining how electrons arrange themselves around nuclei and why different atoms form the bonds that they do. Even the emerging field of quantum computing depends directly on phenomena such as superposition, interference, and entanglement. So this is not a theory sitting quietly at the edge of physics, waiting to be proved. Quantum mechanics works, and that is what makes its central problem so peculiar. Physicists can use quantum theory to calculate the probabilities of experimental results with extraordinary precision. Yet there is still no universally accepted explanation for exactly what happens when one of those possible results becomes the single result that is actually recorded. This is the quantum measurement problem. At its heart lies an uncomfortable mismatch between two apparently different kinds of behaviour. When a quantum system is left to evolve according to the usual equations of quantum mechanics, its state changes smoothly and predictably. The mathematical rule governing this evolution is the Schrödinger equation, named after the Austrian physicist Erwin Schrödinger. Once the initial quantum state is known, the equation determines how that state develops through time. But quantum states do not always describe one definite classical possibility. They can exist in superpositions. A superposition means that several possible outcomes can contribute to the same quantum state at once. An electron might be described by a state containing different possible positions. A particle with quantum spin might be represented as a combination of different possible spin results. A photon travelling through an experiment can have amplitudes associated with more than one path. These alternatives can interfere with one another, which is one reason physicists know that a quantum superposition is not simply ordinary ignorance about which option is secretly true. Then a measurement occurs. Perhaps a photon reaches a detector. Perhaps an electron strikes a screen. Perhaps an apparatus measures the spin of a particle. Before the measurement, the mathematics can contain several possible outcomes. Afterward, the laboratory contains one recorded result. One pixel lights up. One detector clicks. One spin value appears. The great question is what happened between those two descriptions. Textbook quantum mechanics often introduces a second rule known as wavefunction collapse. During measurement, the quantum state is said to change from a superposition of possibilities into a state corresponding to the result that has been observed. But this collapse behaves very differently from ordinary quantum evolution. The Schrödinger equation describes smooth and deterministic evolution. Collapse appears probabilistic. The theory gives probabilities for the possible results, but it does not straightforwardly say which particular result must occur on a particular run. That tension is the heart of the measurement problem. And despite the name, this has very little to do with bad measuring equipment. A detector can be slightly misaligned, a thermometer can be poorly calibrated, a telescope can suffer from noise. Those are ordinary experimental problems, and scientists have spent centuries becoming extremely good at dealing with them. The quantum measurement problem would remain even if the measuring instrument were perfect. Imagine a flawless detector that interacts with a carefully prepared quantum particle exactly as the equations prescribe. The conceptual question would still remain. Why does that interaction produce one definite record rather than a larger quantum state containing several possible records? The puzzle becomes clearer when it is divided into several connected problems. The first concerns why certain kinds of outcomes become special. A quantum state can often be written as a superposition in many different mathematical ways, yet real measuring devices settle into particular stable records. A pointer indicates one position rather than a strange combination of different pointer positions. A detector records a particle in one location rather than displaying a visible interference between macroscopically different readings. Physicists often call this the preferred basis problem. The second question is even more direct. Why does one outcome occur? If the quantum state evolves continuously into a combination containing several possible detector readings, why does an observer experience only one of them? This is sometimes called the definite outcome problem. Then there is the question of probability. Quantum mechanics does not assign equal probabilities to every possibility. Instead, the probability of an outcome is calculated using a rule introduced by the German physicist Max Born. The Born rule connects the mathematical amplitude associated with a possible result to the probability of observing that result. It works extraordinarily well. But depending on how quantum mechanics is interpreted, another question immediately appears. Why should those particular probabilities govern what observers experience? This is why the measurement problem is sometimes described as an embarrassment rather than a crisis. Quantum mechanics is not failing to predict experiments. Quite the opposite. The embarrassment comes from the strange position physics finds itself in after more than a century of success. Scientists possess an immensely powerful mathematical framework, while still disagreeing about what its central measurement process physically represents. Some physicists argue that the wavefunction really does collapse. Others suggest that the equations themselves should be modified so that collapse becomes an objective physical process. Some propose that additional variables exist beneath the ordinary quantum description and determine which outcome actually occurs. Others remove collapse entirely and accept that every possible outcome remains within a larger quantum state. And still others question whether the wave function should be interpreted as a literal physical object at all. These possibilities lead into surprisingly deep questions. Is quantum mechanics a complete description of reality? Does nature contain hidden information that the ordinary theory leaves out? Is there a genuine physical boundary between microscopic quantum systems and macroscopic classical objects? Do all possible outcomes somehow persist? Or have physicists been asking the wrong question by assuming that quantum states describe an observer-independent reality in the same way classical states once seemed to? The awkward secret of quantum mechanics is therefore not that the theory is inaccurate. It is that the theory can be astonishingly accurate while leaving room for radically different pictures of what is actually happening. Somewhere between the smooth evolution of quantum possibilities and the single result appearing in a laboratory, physics encounters a question that has resisted generations of some of its greatest minds. The mathematics tells us what we are likely to see. The detector gives us one answer, and exactly why reality makes that transition remains one of the deepest unresolved problems in modern physics. For most of the history of physics, measurement seemed like a fairly straightforward idea. A property existed whether anyone was looking at it or not, and the purpose of a measuring instrument was simply to reveal what was already there. If you place a thermometer in a room, the temperature does not suddenly spring into existence because you decided to check it. The air already has a temperature. The thermometer responds to it and gives you a reading. If you place an object on a set of scales, its mass was not waiting patiently for the scales to make a decision. The object possessed that mass before the measurement began. The same reasoning applies on much larger scales. An astronomer might observe the position of a planet through a telescope, but the planet does not need the astronomer in order to occupy that position. It continues travelling through space whether anyone happens to be watching. Classical physics was built around this kind of observer-independent picture. Objects have properties. Those properties evolve according to physical laws. Measurements allow us to discover their values. Of course, real measurements are not always perfectly passive. To measure something, an instrument usually has to interact with it. A thermometer exchanges energy with its surroundings before reaching thermal equilibrium. A pressure gauge responds mechanically to collisions between gas molecules and its internal components. Even shining light on a tiny object can transfer energy and momentum to it. So classical physicists were already perfectly familiar with the idea that measurement could disturb what was being measured. But that disturbance was not mysterious. It was simply another physical interaction. If the apparatus were understood in enough detail, then in principle its effect on the system could also be calculated. There was no need to introduce a fundamentally different law of nature that suddenly became active because someone had performed a measurement. This distinction becomes important because quantum mechanics is sometimes introduced as though the entire mystery comes from measuring instruments disturbing very small things. That is not really the issue. The deeper problem concerns what properties a quantum system can meaningfully be said to possess before the measurement takes place. In classical physics, uncertainty usually means incomplete knowledge. Imagine a coin hidden beneath a cup. You do not know whether it landed heads or tails, but you normally assume that one of those outcomes is already true. Your uncertainty belongs to you. It does not belong to the coin. The same principle appears throughout classical statistical mechanics. A container of gas may contain an unimaginably large number of molecules, each moving with its own position and velocity. Tracking every molecule individually would be hopeless in practice, so physicists use probabilities and statistical quantities instead. They calculate distributions of molecular speeds, average energies, pressures and temperatures. But the probability does not usually mean that the molecules somehow lack definite positions or velocities until they are measured. It represents ignorance. The microscopic details are assumed to exist even when nobody knows them. This classical picture is closely connected with the idea of an observer-independent state. At any particular moment, a physical system can in principle be imagined as possessing a complete set of properties. A planet has a position and velocity. A pendulum has an angle and momentum. Every molecule in a gas follows some trajectory. An observer might know those details poorly, or perhaps not at all, but reality itself is still assumed to have settled the matter. Quantum mechanics challenges this idea in a much deeper way. Within quantum theory, probability does not merely appear because an experimenter has failed to collect enough information. Even when the quantum state has been prepared as precisely as the theory allows, the formalism can still assign probabilities to several possible measurement outcomes. That is a very different situation. Consider the quantum property known as spin. If a particle is prepared in a particular quantum state and then measured along a different direction, quantum mechanics may predict several possible results with definite probabilities. The standard theory does not simply say that the particle secretly carried one unknown answer all along and that the apparatus happened to reveal it. Depending on the interpretation of quantum mechanics, the situation before measurement can be considerably stranger than that. This was one of the great conceptual changes that emerged during the development of quantum theory in the early 20th century. Niels Bohr became one of the central figures in trying to understand what this new physics was saying about measurement. Bohr emphasized what he called the quantum postulate, the idea that atomic processes involve a fundamental quantum of action and cannot always be analyzed by imagining a completely independent microscopic object possessing every classical property at once. He also developed the principle of complementarity. Complementarity holds that certain different experimental arrangements can reveal different, mutually exclusive aspects of a quantum system. The famous example concerns wave and particle behaviour. An experiment designed to preserve interference can reveal wave-like behaviour. Another arrangement designed to determine which path a quantum object followed can instead produce definite path information. The important point is not that the particle becomes confused by laboratory equipment. It is that the complete experimental arrangement matters to which physical quantities can be meaningfully assigned definite values. This is a profound departure from classical intuition. In the classical world, we are comfortable imagining that an object carries its properties around with it, rather like labels attached to luggage. The instrument merely reads the labels. Quantum mechanics does not allow that simple picture to survive unchanged. A measurement is not always the passive discovery of a value that unquestionably existed in the same form beforehand. The interaction between the quantum system and the apparatus becomes part of the physical description itself, and that immediately raises a difficult question. If measurement is no longer simply revealing an already settled reality, what exactly is it doing? Classical physics allowed uncertainty to remain safely inside the observer's knowledge. Quantum mechanics places probability inside the fundamental mathematical description. That shift is easy to state, but its consequences are enormous. The old distinction between what exists and what we merely happen to know becomes much harder to maintain. And once measurement stops being nothing more than opening an envelope to see the answer already written inside, physics must confront the far stranger possibility that the act of obtaining a definite result is itself something that needs to be explained. For most of the history of physics, measurement seemed like a fairly straightforward idea. A property existed, whether anyone was looking at it or not, and the purpose of a measuring instrument was simply to reveal what was already there. If you place a thermometer in a room, the temperature does not suddenly spring into existence because you decided to check it. The air already has a temperature. The thermometer responds to it and gives you a reading. If you place an object on a set of scales, its mass was not waiting patiently for the scales to make a decision. The object possessed that mass before the measurement began. The same reasoning applies on much larger scales. An astronomer might observe the position of a planet through a telescope, but the planet does not need the astronomer in order to occupy that position. It continues travelling through space whether anyone happens to be watching. Classical physics was built around this kind of observer-independent picture. Objects have properties. Those properties evolve according to physical laws. Measurements allow us to discover their values. Of course, real measurements are not always perfectly passive. To measure something, an instrument usually has to interact with it. A thermometer exchanges energy with its surroundings before reaching thermal equilibrium. A pressure gauge responds mechanically to collisions between gas molecules and its internal components. Even shining light on a tiny object can transfer energy and momentum to it. So classical physicists were already perfectly familiar with the idea that measurement could disturb what was being measured. But that disturbance was not mysterious. It was simply another physical interaction. If the apparatus were understood in enough detail, then in principle its effect on the system could also be calculated. There was no need to introduce a fundamentally different law of nature that suddenly became active because someone had performed a measurement. This distinction becomes important because quantum mechanics is sometimes introduced as though the entire mystery comes from measuring instruments disturbing very small things. That is not really the issue. The deeper problem concerns what properties a quantum system can meaningfully be said to possess before the measurement takes place. In classical physics, uncertainty usually means incomplete knowledge. Imagine a coin hidden beneath a cup. You do not know whether it landed heads or tails, but you normally assume that one of those outcomes is already true. Your uncertainty belongs to you. It does not belong to the coin. The same principle appears throughout classical statistical mechanics. A container of gas may contain an unimaginably large number of molecules, each moving with its own position and velocity. Tracking every molecule individually would be hopeless in practice, so physicists use probabilities and statistical quantities instead. They calculate distributions of molecular speeds, average energies, pressures, and temperatures. But the probability does not usually mean that the molecules somehow lack definite positions or velocities until they are measured. It represents ignorance. The microscopic details are assumed to exist even when nobody knows them. This classical picture is closely connected with the idea of an observer-independent state. At any particular moment, a physical system can in principle be imagined as possessing a complete set of properties. A planet has a position and velocity. A pendulum has an angle and momentum. Every molecule in a gas follows some trajectory. An observer might know those details poorly, or perhaps not at all, but reality itself is still assumed to have settled the matter. Quantum mechanics challenges this idea in a much deeper way. Within quantum theory, probability does not merely appear because an experimenter has failed to collect enough information. Even when the quantum state has been prepared as precisely as the theory allows, the formalism can still assign probabilities to several possible measurement outcomes. That is a very different situation. Consider the quantum property known as spin. If a particle is prepared in a particular quantum state and then measured along a different direction, quantum mechanics may predict several possible results with definite probabilities. The standard theory does not simply say that the particle secretly carried one unknown answer all along and that the apparatus happened to reveal it. Depending on the interpretation of quantum mechanics, the situation before measurement can be considerably stranger than that. This was one of the great conceptual changes that emerged during the development of quantum theory in the early 20th century. Niels Bohr became one of the central figures in trying to understand what this new physics was saying about measurement. Bohr emphasized what he called the quantum postulate, the idea that atomic processes involve a fundamental quantum of action and cannot always be analyzed by imagining a completely independent microscopic object possessing every classical property at once. He also developed the principle of complementarity. Complementarity holds that certain different experimental arrangements can reveal different, mutually exclusive aspects of a quantum system. The famous example concerns wave and particle behaviour. An experiment designed to preserve interference can reveal wave-like behaviour. Another arrangement designed to determine which path a quantum object followed can instead produce definite path information. The important point is not that the particle becomes confused by laboratory equipment. It is that the complete experimental arrangement matters to which physical quantities can be meaningfully assigned definite values. This is a profound departure from classical intuition. In the classical world, we are comfortable imagining that an object carries its properties around with it, rather like labels attached to luggage. The instrument merely reads the labels. Quantum mechanics does not allow that simple picture to survive unchanged. A measurement is not always the passive discovery of a value that unquestionably existed in the same form beforehand. The interaction between the quantum system and the apparatus becomes part of the physical description itself, and that immediately raises a difficult question. If measurement is no longer simply revealing an already settled reality, what exactly is it doing? Classical physics allowed uncertainty to remain safely inside the observer's knowledge. Quantum mechanics places probability inside the fundamental mathematical description. That shift is easy to state, but its consequences are enormous. The old distinction between what exists and what we merely happen to know becomes much harder to maintain. And once measurement stops being nothing more than opening an envelope to see the answer already written inside, physics must confront the far stranger possibility that the act of obtaining a definite result is itself something that needs to be explained. Imagine a single microscopic particle entering a measuring device designed to answer one very simple question. Its quantum spin will be measured along a particular direction, and the apparatus has only two possible readings: upward or downward. The word spin can be slightly misleading. A quantum particle is not necessarily a tiny ball physically rotating on an axis. Spin is an intrinsic form of angular momentum built into the quantum description of particles, and when the spin of certain particles is measured along a chosen direction, only specific discrete results are obtained. Suppose the particle has been prepared in a superposition of the two possible spin results. Before measurement, its quantum state therefore contains an upward component and a downward component. Now imagine that the measuring apparatus begins in a neutral state. Its pointer has not moved. Its display has not yet shown anything. Nothing has been recorded. If quantum mechanics applies to both the particle and the apparatus, their interaction can be described by the same smooth Schrödinger evolution that governs other quantum systems. And this is where something interesting happens. The upward component of the particle becomes correlated with an apparatus displaying upward. The downward component becomes correlated with an apparatus displaying downward. The original superposition has not simply vanished. Instead, it has spread. The particle and measuring device now form what quantum mechanics calls an entangled state. Entanglement means that the quantum descriptions of the two systems can no longer be treated independently. The state of the particle has become correlated with the state of the apparatus. The upward spin is associated with an upward reading. The downward spin is associated with a downward reading. Taken together, the complete state contains both correlated alternatives. This sounds superficially similar to an ordinary situation in which one result has happened, but the scientist simply does not know which one. But the difference is crucial. Imagine placing a coin beneath a cup after tossing it. The coin is either heads or tails. You may not know which, but one result has already occurred. That is a classical mixture of possibilities. The uncertainty represents incomplete information. Quantum superposition is different. Before anything destroys the coherence between its components, the full quantum state retains the different alternatives as parts of one mathematical state. Their relative phases can matter, and under appropriate conditions the alternatives can interfere. So saying that the particle and apparatus are entangled does not merely mean that the detector secretly chose one result while the physicist remains ignorant of it. The standard unitary evolution still contains both correlations. One part describes spin upward with an upward record, another describes spin downward with a downward record. Nothing in that evolution has yet selected either one as uniquely real. Perhaps the apparatus simply needs to become larger. That seems like a natural thought. A microscopic particle might behave strangely, but surely a substantial laboratory detector will force matters to become definite. Unfortunately, making the apparatus larger does not automatically solve the problem. Suppose the detector sends its result to a computer. When the detector is correlated with the upward result, the computer memory records upward. When the detector is correlated with downward, the computer records downward. If the computer is also treated as a quantum system, the entanglement simply spreads again. Now the state contains one correlated alternative involving the particle, detector, and computer all recording upward, alongside another involving all three recording downward. We might add a printer. The same reasoning applies. We could add a camera pointed at the screen. Again, the camera becomes correlated with the possible records. The electronic circuitry in the room responds differently depending on the detector state. Photons bouncing from the display carry information away. Air molecules collide with the equipment. Heat escapes into the surroundings. Rather than drawing a firm boundary around the original particle, the quantum correlations seem capable of expanding outward. The measuring apparatus is not exempt from physics, merely because it has buttons, wires, and an inconvenient number of screws. It is made from atoms. Those atoms contain electrons and nuclei. Those particles are described by quantum mechanics. Treating a measuring device quantum mechanically is therefore not an exotic philosophical indulgence. It follows naturally from taking seriously the idea that quantum theory describes physical matter universally. If electrons obey quantum mechanics inside an isolated experiment, there is no obvious reason why they should stop obeying it once somebody arranges enough of them into a detector. This creates what is sometimes called a measurement chain. A microscopic system interacts with the apparatus. The apparatus influences a recording device. The recording device interacts with the surrounding room. Information about the possible outcomes becomes distributed across more and more physical degrees of freedom. The German physicist Heinz-Dieter Zeh developed some of the earliest systematic work showing how interactions with the environment transform the appearance of quantum superpositions on macroscopic scales. Later, the physicist Wojciech Zurek greatly developed this program through the theory of environmental decoherence and environment-induced selection. Their work helped explain something that had long seemed mysterious. Macroscopic superpositions become extraordinarily difficult to observe because ordinary objects are almost never isolated. Every moment they interact with vast numbers of environmental particles. Air molecules scatter from them. Photons strike and leave them. Thermal radiation carries information away. These interactions entangle the system with its surroundings extremely rapidly. The relative phase information needed to observe interference between different macroscopic possibilities becomes dispersed through the environment. From the perspective of someone examining only the apparatus, interference between those alternatives can effectively disappear. This is one of the reasons the everyday world looks so thoroughly classical. A detector pointer does not normally appear as a shimmering combination of several positions. A computer display does not visibly interfere with another version of itself, displaying a different result. Environmental interactions suppress that kind of observable quantum behaviour with remarkable efficiency. But there is a subtle distinction hiding here. Explaining why different macroscopic alternatives stop interfering is not necessarily the same as explaining why only one of them actually occurs. The total quantum description can still contain the correlated alternatives, now entangled with an enormous environment. One alternative may contain a particle measured upward, a detector reading upward, a computer storing upward, and countless surrounding particles carrying information about upward. Another may contain the corresponding downward records. Decoherence can make those alternatives behave almost as though they belong to separate classical possibilities. It can explain why we do not normally observe interference between them. What it does not automatically do is point to one component of the total state and declare that this one alone became reality. That distinction is easy to overlook because, experimentally, the disappearance of interference is enormously important. It explains much of the transition from delicate microscopic quantum behaviour to the stable records of ordinary laboratory equipment. Yet the original question remains quietly underneath. The particle became entangled with the detector. The detector became entangled with the computer. The computer became entangled with the surrounding room. The quantum correlations spread farther and farther outward. And still, when someone eventually checks the experiment, there is not a vague cloud of readings. There is one result. The appearance of a classical world can be explained to a remarkable degree by the way quantum systems interact with their environments. Why that world appears to contain one uniquely experienced outcome is a separate question, and it is precisely there that the measurement problem refuses to disappear. One of the most remarkable features of quantum mechanics is that it does not usually tell us exactly what will happen in a single experiment. Instead, it tells us the odds. That idea became central to quantum theory in 1926, when the German physicist Max Born proposed a probabilistic interpretation of the wavefunction. At the time, quantum mechanics was still very new. Physicists such as Werner Heisenberg, Erwin Schrödinger, Niels Bohr, and Max Born were developing mathematical descriptions that could explain the strange behaviour of atoms, electrons, and light. The equations were working. What remained much less obvious was what their mathematical quantities actually meant. The wavefunction could evolve smoothly according to the Schrödinger equation. It could contain several possible outcomes in a superposition. It could produce interference when different amplitudes combined. But how should that wavefunction be connected to what an experimenter actually sees? Max Born supplied one of the most important answers. The wavefunction itself should not normally be interpreted as a simple physical wave showing where a particle is spread out in the same way that a water wave spreads across a pond. Instead, the mathematical amplitude associated with each possible outcome can be used to calculate the probability of obtaining that outcome. The rule is straightforward in principle. The probability of a particular result is given by the squared magnitude of the quantum amplitude associated with that result. This became known as the Born rule. It is difficult to overstate how important this rule is. Without it, the wave function would describe a collection of mathematical possibilities without telling physicists how those possibilities connect to actual observations. The Born rule turns the abstract quantum state into experimental predictions. Imagine firing particles one at a time toward a detector screen. Quantum mechanics can assign an amplitude to every possible position where a particle might arrive. In some regions of the screen, the amplitude will have a larger magnitude. In others, it will be smaller. The Born rule converts those amplitudes into a probability distribution. A region associated with a larger squared amplitude is more likely to register the particle. A region associated with a smaller squared amplitude is less likely. Yet when the experiment is actually performed, the particle does not usually arrive as a faint mist spread smoothly across the detector. One detection appears at one location, perhaps one pixel illuminates, perhaps one atom inside a photographic plate changes state, perhaps one electronic signal is produced. That single result can appear unpredictable. Repeat the experiment many times, however, preparing the particle in the same way each time, and a pattern begins to emerge. The individual events accumulate. Some regions receive many detections, others receive very few. After enough repetitions, the statistical distribution approaches the probabilities predicted by the Born rule. This is one of the great triumphs of quantum theory. It does not merely say that the result is uncertain, it tells us how uncertain. If two outcomes are predicted to occur with probabilities of roughly 1/2 each, then repeated experiments produce frequencies close to that division. If one result has a probability of only a few percent, it appears rarely but at approximately the expected rate over sufficiently many trials. Quantum experiments performed across atomic physics, particle physics, optics, and other fields repeatedly confirm this statistical structure. The probabilities are not decorative additions to the theory, they are among its most precisely tested predictions. But there is a subtle gap between predicting the odds and explaining the event. Suppose quantum mechanics says that one detector has a probability of roughly 3/4 of clicking, while another has a probability of roughly 1/4. The Born rule tells us how the results should be distributed across many repetitions. It does not tell us why, on one particular run, the first detector clicked. The numbers describe the chances. They do not obviously describe a physical mechanism that chooses one possibility. That difference becomes especially important in the measurement problem. Before measurement, the quantum state can contain amplitudes associated with several outcomes. The Born rule tells us how much probability to assign to each. Then the experiment produces one result. The rule predicts the statistics beautifully, but it does not by itself explain how a superposition containing several possibilities becomes the single recorded event sitting in the laboratory. That is already puzzling in textbook quantum mechanics. It becomes even more interesting in interpretations that insist the universal wave function always evolves smoothly and never truly collapses. If the Schrödinger equation governs everything, then the evolution of the complete quantum state is deterministic. The initial wave function fixes how all of its branches and amplitudes develop. No random selection is inserted into the underlying unitary evolution. This raises what is often called the probability problem. If every possible measurement result remains somewhere within the evolving quantum state, why should an observer expect experiences to occur with frequencies given by the Born rule? Why should the squared amplitudes carry precisely the statistical significance that experiments reveal? Different interpretations offer different answers. Some treat the Born rule as a fundamental probability law accompanying genuine collapse. Some try to derive it from deeper assumptions about rational expectation, symmetry, typicality, or the structure of the quantum state. Others interpret quantum probabilities as reflecting an observer's expectations rather than objective chances existing independently in nature. But the empirical rule itself remains extraordinarily robust. Prepare the same quantum state again and again, perform the same measurement, and the frequencies settle toward the predicted values. This gives quantum mechanics a curious combination of certainty and uncertainty. The theory can be exceptionally precise about probability, while remaining silent about which individual result will appear. It can say that one outcome should happen about 90 times in every 100 repetitions, without telling you whether the very next trial will be one of those 90. And this is why Max Born's rule does not remove the measurement problem. In some ways it sharpens it. The rule gives physics a precise mathematical bridge from the wave function to experimental statistics. It explains how strongly each possible outcome should be weighted. What it does not provide is a physical description of one possibility becoming the event that is actually recorded. Quantum mechanics can therefore tell us the odds with astonishing accuracy. It can predict the pattern formed by thousands or millions of measurements. It can describe exactly how probability is distributed among the alternatives. And yet, when one detector finally clicks, the theory still leaves room for the deeper question. Why that result? Why only one? And what physically turned a set of weighted possibilities into the single event that appeared? Textbook quantum mechanics introduces a remarkably direct answer to the question of how many possibilities become one observed result. The wave function collapses. Before measurement, a quantum system may be described by a superposition containing several possible outcomes. After measurement, the state is replaced by one associated with the result that has actually been recorded. This rule is often called wave function collapse, state reduction, or the projection postulate. It sounds simple enough. The difficulty is that collapse behaves very differently from the ordinary evolution of a quantum state. When an isolated system evolves according to the Schrödinger equation, its development is continuous and deterministic. Once the initial state and the relevant physical conditions are specified, the equation determines the later state. That evolution is also reversible in principle. If the complete state of an isolated quantum system could be controlled with perfect accuracy, the mathematical evolution could be run backwards. Collapse does not behave like that. Suppose a particle is in a superposition of two possible spin results. A measurement is performed, one result appears, the state is then replaced by a state corresponding to that particular outcome. Which outcome occurs is not determined in advance by the Schrödinger equation. Instead, the probabilities are supplied by the Born rule. The change is therefore probabilistic. In the ideal textbook formulation, it is also effectively discontinuous. The quantum state does not smoothly flow from a superposition into one selected component through ordinary Schrödinger evolution. The measurement rule simply tells us to replace the previous state with the state matching the observed result. And once that has happened, the process is not generally reversible. If a measurement has reduced a superposition to one definite result, simply running the Schrödinger equation backwards does not reconstruct the original superposition. Quantum mechanics therefore seems to contain two different rules for changing a state. One governs ordinary evolution, the other governs measurement. That is the formal tension sitting at the centre of the measurement problem. Several of the founders of quantum theory helped shape the mathematical language used to describe this process. Paul Dirac developed an elegant framework for quantum states and observables, and treated measurement as producing definite eigenvalues associated with the quantities being observed. John von Neumann gave one of the most systematic early mathematical accounts of quantum measurement. His formulation distinguished the ordinary unitary evolution of a quantum system from the non-unitary state reduction associated with a measurement outcome. Gerhard Elders later refined the state update rule, particularly for measurements in which more than one quantum state can correspond to the same measured value. These historical formulations are related, but they are not completely identical. Modern discussions often group them loosely under labels such as the projection postulate, even though the details of how states are updated can differ depending on the type of measurement. The central physical idea remains familiar. Once an ideal measurement produces a particular value, the post-measurement state should normally be correlated with that result. Repeated measurement makes the point especially clear. Suppose the spin of a particle is measured along a particular direction and the result is upward. If the same ideal measurement is immediately repeated, quantum mechanics predicts that upward should be obtained again with certainty, provided nothing has disturbed the particle between measurements. The first measurement has therefore done more than merely display a number. The state used to describe the system afterward is now associated with the recorded value. That rule is extremely useful. It is also conceptually strange. What exactly happened during the first measurement? One possibility is that collapse is an objective physical process. On this view, the wavefunction genuinely changes in the world when a measurement occurs. Several possibilities are reduced to one actual outcome. But if collapse is physical, another question immediately appears. What causes it? Is there some particular size an apparatus must reach? Does collapse occur when information becomes permanently recorded? Does it depend on irreversibility? Does an environment trigger it? Or is there a new law of nature operating alongside the Schrödinger equation? Another possibility is that collapse is not a physical event at all. Perhaps it simply represents an update in information. Before looking at the detector, an observer assigns several possible outcomes. After seeing the result, the observer updates the quantum state to reflect what is now known. This makes collapse resemble ordinary probability updating. Learning that a hidden playing card is a queen changes your probability assignments, but nothing mystical happens to the card itself. Some interpretations of quantum mechanics move in this direction. Others argue that collapse is an effective description of a much larger physical interaction involving the system, apparatus, and environment. From this perspective, the simple textbook collapse rule might be a convenient shortcut rather than a fundamental process. Each possibility carries a different view of what the wave function itself represents. Is it a real physical object? A description of information? A catalogue of probabilities? A compact mathematical device for predicting observations? The collapse question cannot be separated completely from those deeper questions. There is also a particularly stubborn problem hidden in the ordinary phrase that collapse happens when a measurement is made. What counts as a measurement? A detector interacting with an electron is certainly a physical interaction, but so is an electron colliding with another electron. A photon striking a photographic plate is an interaction. A photon striking a dust grain is also an interaction. Why should one produce collapse while the other merely produces ordinary quantum entanglement? If the answer is that a sufficiently large apparatus causes collapse, then the theory needs some way of defining sufficiently large. If the answer involves an observer, it must explain exactly what physical feature of an observer matters. If the answer is that measurement creates a permanent record, then permanence itself must be defined using physics rather than everyday intuition. Simply saying that collapse happens during measurement, therefore, does not fully solve the mystery. It can merely move the mystery into the word measurement. The textbook rule tells physicists how to calculate what happens after an outcome has been obtained. It works extremely well. But a successful instruction for updating the mathematics is not automatically an explanation of the physical process underneath it. Quantum mechanics therefore seems to offer two remarkably effective forms of evolution. Smooth Schrödinger evolution describes the unfolding of possibilities. Collapse describes the appearance of one result. The awkward question is why nature should need both, and exactly where one is supposed to give way to the other. John von Neumann gave quantum measurement one of its most systematic early mathematical treatments. Rather than treating measurement as a mysterious moment in which a scientist simply looks at something and obtains an answer, von Neumann considered the physical chain of interactions connecting a microscopic system to the final recorded result. Imagine again a single quantum particle. Perhaps its spin is being measured. The particle enters a detector, and the detector is designed so that different possible spin values produce different physical responses. If the spin is measured as upward, one part of the apparatus responds. If it is measured as downward, another response occurs. The important point is that the particle does not communicate its result through anything magical. It interacts physically with the apparatus. The measurement begins as a coupling between two physical systems. John von Neumann described an idealized form of this process, in which the value of the quantity being measured becomes correlated with the position of a pointer. The pointer does not need to be a literal needle on a dial. It can represent any macroscopic record capable of taking distinguishable states. One possible value of the particle becomes correlated with one pointer position, another possible value becomes correlated with another. This model became extremely influential because it turns measurement into an interaction that can itself be described mathematically. But once the apparatus has registered something, the process does not necessarily end there. The detector may send an electrical signal to a recording device. The recording device may store the result in computer memory. A display may illuminate. Light from that display may enter the eye of an observer. Signals then travel through the nervous system and are processed by the brain. The original microscopic event has now become connected to a long chain of physical systems: particle, detector, recording device, display, eye, nervous system, brain. At every stage, information about the possible result is passed onward. This became known as the von Neumann chain. And the chain creates a rather uncomfortable question. Where exactly should the quantum description stop? Suppose the particle is treated quantum mechanically, but the detector is treated as a classical object. Then the boundary lies between the particle and the apparatus. But there is no obvious reason why that boundary must stay there. The detector is itself made from atoms and particles, so perhaps the detector should also be included in the quantum description. Now the boundary is moved farther outward. The particle and detector are treated as one combined quantum system, while the recording device remains outside. But the recording device is also made from physical matter. It can be included too. The same can be done with the display. And the observer's sensory organs, and, at least in principle, the physical processes inside the brain. This flexibility is often described as a movable cut between the part of the experiment treated quantum mechanically and the part treated as the apparatus or observer. For ordinary laboratory predictions, moving that cut usually does not change what probabilities are eventually calculated for the measured results. That is useful experimentally. Conceptually, however, it creates another problem. Moving the boundary does not tell us where a real physical collapse actually happens. If the detector is included in the quantum system, then it can become entangled with the particle. If the recording device is added, it can become entangled with both. If the observer's physical state is included as well, then the ordinary unitary mathematics can continue extending the correlations. One alternative contains a particle with one spin result, a detector showing that result, a computer storing it, and an observer correlated with that record. Another alternative contains the corresponding chain for the other possible result. Simply adding more objects does not automatically create a unique outcome. It makes the quantum description larger. This is one reason the measurement problem cannot be solved merely by pointing toward a sufficiently complicated machine and calling it classical. A measuring apparatus is not fundamentally made from different ingredients than the object it measures. Both belong to the same physical universe. Von Neumann's framework also highlights an important distinction between two different meanings of state change. Suppose an observer learns that the detector recorded upward. For calculating everything that follows, it is perfectly sensible to condition the quantum state on that known result. The observer now uses the state associated with upward, because upward is the result that was obtained. As a mathematical procedure, this is enormously useful. But that does not automatically answer the deeper physical question. Did the wavefunction itself literally collapse in the world? Did every other component physically disappear? Or did the mathematical state merely change because the observer acquired new information? Those are different claims. One concerns how calculations should be updated after a result is known. The other concerns what objectively happened to reality. Quantum mechanics is exceptionally good at the first task. The second remains controversial. And this is what makes the measurement chain so revealing. The theory can describe in extraordinary detail how microscopic alternatives become correlated with larger and larger physical systems. It can describe the particle interacting with the detector. It can describe the detector influencing the computer. It can even, in principle, include parts of the observer within the same quantum description. What the ordinary unitary evolution does not obviously provide is the moment when that expanding collection of correlated possibilities becomes one uniquely experienced record. The chain can be extended almost as far as one wishes. The quantum alternatives can travel with it. And somewhere along that chain, everyday experience insists that there is only one answer. Exactly why remains the uncomfortable part. For much of the 20th century, the most widely taught way of talking about quantum mechanics was associated with what came to be called the Copenhagen interpretation. That name can be slightly misleading. There was never one perfectly unified Copenhagen doctrine written down and accepted in exactly the same form by everyone involved. Instead, the term refers to a family of closely related views shaped especially by Niels Bohr and Werner Heisenberg, along with other physicists working during the early development of quantum theory. Their central concern was practical as much as philosophical. Quantum mechanics had produced a new mathematical framework that described atoms and particles with extraordinary success. But the concepts inherited from classical physics no longer seemed capable of describing every aspect of microscopic reality at once. Niels Bohr responded by placing enormous emphasis on the experimental arrangement itself. For Bohr, the outcome of an experiment had to be expressed in clear classical language. A detector must have a definite position. A measuring device must have a definite arrangement. A result must leave an unambiguous record that can be communicated to other scientists. This did not mean that Bohr believed the microscopic world was secretly classical underneath quantum theory. Quite the opposite. He argued that the quantum nature of atomic processes placed fundamental limits on the kinds of descriptions that could be meaningfully combined. One of his most important ideas was complementarity. Complementarity says that different experimental arrangements can reveal different aspects of a quantum system, even when those arrangements cannot be used simultaneously. The classic example involves wave-like interference and particle-like path information. Suppose a quantum particle passes through an apparatus containing two possible routes. If the experiment is arranged so that no information reveals which route the particle followed, the amplitudes associated with the two paths can interfere. An interference pattern may appear, but if the apparatus is modified so that reliable path information is obtained, the conditions required for that interference are changed. The experiment now reveals a different kind of information. For Bohr, these were not two incomplete glimpses of an ordinary classical object that secretly possessed all of its properties in a familiar way. There were complementary experimental contexts. Each arrangement allowed certain quantities to be meaningfully defined and measured. The arrangement itself therefore became an essential part of describing the phenomenon. Werner Heisenberg approached some of the same issues with slightly different emphasis. He often spoke about a division between the quantum system being studied and the apparatus used to observe it. On one side of this division, quantum states and probabilities were used. On the other, the apparatus was described in the ordinary classical terms required to state what had actually happened. Importantly, this division did not have to sit at one permanently fixed physical location. The boundary could be shifted. A detector might initially be treated classically, but if greater detail were required, part of that detector could itself be included within the quantum description, and the dividing line could be moved farther outward. This resembles the movable cut that appears in broader discussions of measurement. It also helps avoid one of the most common oversimplifications surrounding the Copenhagen interpretation. The theory does not require the idea that human consciousness possesses some mysterious power that forces the universe to choose an answer merely by looking at it. Historical discussions of observers were sometimes ambiguous, and later physicists explored stronger consciousness-based proposals, but the central Copenhagen ideas do not depend on a mind magically collapsing a wave function. The emphasis is instead on the physical experimental context and on the definite record through which the result becomes meaningful. This also allows a more operational reading of the wave function. Rather than insisting that the wave function must be a literal physical substance spread through ordinary space, one can treat it primarily as a mathematical tool for organizing predictions. The quantum state tells us which measurement outcomes are possible, and what probabilities should be assigned to them. Once the experimental arrangement is specified, the formalism provides predictions for the observations that can be made. From this practical point of view, demanding a detailed picture of what the wave function is doing between observations may be asking more of the theory than it was designed to provide. For generations of physicists, this attitude was extremely productive. A researcher could prepare a quantum state, calculate its evolution, apply the Born rule, and compare the predicted probabilities with experimental results. The method worked. Semiconductors did not refuse to function until everyone agreed on ontology. Lasers did not wait for a philosophical consensus. Atomic spectra remained stubbornly measurable. The Copenhagen style therefore encouraged physicists to concentrate on what could be prepared, measured, predicted, and communicated. That practical success explains much of its historical influence. But the measurement problem does not disappear simply because calculations proceed smoothly. The difficulty returns when the classical apparatus itself is examined closely. A detector is made from atoms. Its pointer consists of molecules. Its electronics depend on electrons moving through materials. Every component that produces the supposedly classical record is ultimately constructed from the same quantum ingredients as the particle being measured. So why should one part of nature require quantum description while another part is granted definite classical properties? Bohr's answer was largely conceptual rather than microscopic. A classical description is required for the experimental conditions and the recorded outcome, because otherwise the meaning of the measurement would become ambiguous. But this still leaves a deeper physical question. What mechanism produces that classical definiteness? If the detector can itself be described quantum mechanically, why does it not simply become entangled with the different possible outcomes? If the boundary between quantum system and classical apparatus can move, why does reality not seem to care where the physicist draws it? This is the enduring strength and weakness of the Copenhagen approach. It gives quantum mechanics a disciplined language for connecting experiments with predictions. It reminds us that measurements occur in concrete physical arrangements rather than in an abstract vacuum. It also avoids pretending that classical concepts can be carried unchanged into every microscopic situation. Yet it leaves the boundary between quantum possibility and classical fact partly built into the description, rather than derived from a universally agreed physical process. For practical physics, that may often be enough. For the measurement problem, it is precisely where the discomfort begins. Few thought experiments in physics are as famous as Schrödinger's cat. It is also one of the most frequently misunderstood. Erwin Schrödinger introduced the idea in 1935, not because he believed ordinary cats actually spend their afternoons suspended in a visible mixture of life and death, but because he wanted to expose how strange quantum theory becomes when its rules are extended from microscopic systems to familiar macroscopic objects. The setup begins with a quantum event. Imagine a radioactive atom sealed inside a box. During a certain interval of time, the atom has some probability of decaying and some probability of remaining unchanged. A detector is arranged to register whether the decay occurs. That detector is connected to a mechanism containing poison. If the atom decays, the detector triggers the mechanism, the poison is released, and the cat dies. If the atom does not decay, nothing happens, and the cat remains alive. The important part is the chain of correlations. The state of the atom becomes connected to the state of the detector. The detector becomes connected to the poison mechanism, and the poison mechanism becomes connected to the condition of the cat. If the entire system is treated according to ordinary unitary quantum evolution, then the initial superposition associated with a radioactive atom does not necessarily disappear when it reaches the detector. Instead, the alternatives become entangled. One component contains an undecayed atom, an inactive detector, an unreleased poison, and a living cat. Another contains a decayed atom, a triggered detector, released poison, and a dead cat. The strange conclusion is not that anyone expects to open an ordinary box and see a cat somehow shimmering between two biological conditions. The point is that if the mathematical rules of quantum mechanics apply universally, it becomes difficult to identify precisely where the microscopic superposition is supposed to stop. Perhaps it stops at the detector. Perhaps at the poison mechanism. Perhaps when the cat becomes involved. But simply naming a larger object does not explain why the quantum description should suddenly change. Schrödinger was deliberately making the problem absurdly visible. A superposition that seems tolerable when attached to a single atom becomes much harder to ignore when its alternatives have been amplified into something unmistakably macroscopic. The cat therefore turns the measurement problem into a question that cannot easily be dismissed as a peculiarity of particles too small to see. The same underlying tension appears in another famous scenario associated with the physicist Eugene Wigner. Wigner's friend replaces the cat with an observer. Imagine a scientist inside a sealed laboratory performing a quantum measurement. From the friend's perspective, the experiment produces one definite result. Perhaps the detector records upward spin. The friend sees that outcome and writes it down. For the person inside the room, nothing appears ambiguous. But now imagine Eugene Wigner standing outside the sealed laboratory. If Wigner treats the entire room as one isolated quantum system, then in principle he might describe the friend, detector, and particle together. Under purely unitary evolution, the outside description could contain one component in which the friend observed upward, and another in which the friend observed downward. That creates an uncomfortable mismatch. Inside the laboratory, the friend seems to possess one definite experience. Outside, Wigner may assign a superposition to the whole laboratory. So when did collapse occur? Did it happen when the detector registered a result? Did it occur when the friend became aware of that result? Does it happen only when Wigner opens the laboratory? Could the friend and Wigner legitimately assign different quantum states at the same time? Or, in an interpretation without fundamental collapse, does no physical collapse happen anywhere? The thought experiment became particularly significant because it pushed the measurement chain into the observer. Once the observer is treated as another physical system, the old habit of placing the observer safely outside quantum mechanics becomes difficult to maintain. Historically, this helped encourage speculation about whether consciousness itself might play a special role in collapse. Some proposals suggested that a quantum state remains in superposition until a conscious observer becomes aware of a result. That idea has become deeply associated with popular discussions of quantum mechanics, but it is important not to mistake it for a general requirement of the theory. Most contemporary approaches to quantum measurement do not require human consciousness to possess a unique physical power. Environmental decoherence, objective collapse models, Bohmian mechanics, Everettian interpretations, relational approaches, and many other frameworks attempt to understand measurement without making consciousness the fundamental switch that turns possibility into reality. The observer problem has nevertheless refused to disappear. A more recent and sophisticated example was developed by Daniela Frocchia and Renato Renner. Their thought experiment combines several observers reasoning about quantum systems and about one another's measurement results. Under a particular collection of assumptions, including universal applicability of quantum theory, consistency between the conclusions of different agents, and the existence of single outcomes, the reasoning can lead to a contradiction. The result generated considerable debate because the meaning of the assumptions and what exactly must be abandoned depends strongly on how quantum theory is interpreted. Some physicists see such arguments as evidence that ordinary single-outcome reasoning cannot simply be combined with universal unitary quantum mechanics. Others argue that the contradiction reflects incompatible perspectives, inappropriate combinations of quantum descriptions, or assumptions that particular interpretations need not accept. What the scenario does not provide is a universally agreed experimental proof that one interpretation is correct. Instead, it sharpens the conceptual pressure. Schrödinger's cat asks how a microscopic superposition can become connected to a macroscopic fact. Wigner's friend asks what happens when the macroscopic fact belongs to an observer who is himself treated quantum mechanically. And extended observer scenarios ask whether several such observers can consistently reason about one another, while all remaining inside the same universal theory. Each version makes the same underlying discomfort harder to hide. Quantum mechanics can describe the correlations spreading outward with extraordinary precision. But once those correlations include detectors, laboratories, memories, and observers, the question of what counts as one definite fact becomes increasingly difficult to avoid. The cat was never really the problem. The problem was always the boundary between quantum possibility and experienced reality. At first glance, the measurement problem seems to invite a very simple escape. Perhaps quantum mechanics looks probabilistic only because it is incomplete. Maybe every measurable property already possesses a definite value before the experiment begins, and the apparatus merely reveals that hidden value. In that picture, a particle measured with spin upward was always going to produce upward. A particle detected on the left side of a screen was already destined for the left. The wavefunction would then describe incomplete knowledge rather than a genuinely unresolved collection of possibilities. This would make quantum measurement feel much more like classical measurement. The thermometer would simply be reading the temperature. The detector would simply be reading the particle. The mystery would shrink considerably. The difficulty is that nature does not allow this classical rescue in such a straightforward form. One of the most important examples comes from the physicist David Bohm. In the early 1950s, Bohm developed a hidden variable formulation of quantum mechanics in which particles possess definite positions at all times. The wavefunction still exists and still evolves according to the Schrödinger equation, but it also guides the actual configuration of the particles. This showed something important. Hidden variables themselves are not forbidden. It is possible to construct a theory with additional underlying quantities that reproduces the usual predictions of quantum mechanics. But Bohm's theory comes with a substantial price. It is explicitly non-local. The behaviour of one part of an entangled system can depend on the configuration of distant parts in a way that cannot be understood through the ordinary classical picture of influences travelling only between nearby objects. That feature became especially significant after the work of John Stuart Bell. In 1964, Bell demonstrated one of the most profound results in the foundations of physics. He considered theories in which measurement outcomes are determined by underlying variables while influences remain local in the relevant sense. From these assumptions, Bell derived mathematical limits on the correlations that distant measurements could display. These limits became known as Bell inequalities. Quantum mechanics predicts that certain entangled systems can violate those inequalities. Experiments have repeatedly found correlations consistent with the quantum predictions. The conclusion must be stated carefully. Bell's theorem does not prove that particles cannot possess any hidden properties. It does not prove that David Bohm's theory is impossible. And it does not prove that measurement has somehow been solved. What it rules out is a broad class of theories that try to preserve both a sufficiently strong form of locality and predetermined outcomes of the relevant kind, while reproducing all quantum correlations. In simple terms, nature cannot be restored to the most comfortable classical picture merely by imagining that every particle carries a small secret instruction sheet telling it how to respond to every possible measurement, while everything remains locally independent. Something has to give. David Bohm's approach keeps definite particle positions. It gives up locality. Other interpretations make different sacrifices. Bell's result is therefore less like a complete answer and more like a narrowing of the available escape routes. Another major restriction came from the work of Simon Kochen and Ernst Specker. Their theorem concerns contextuality. Suppose we once again try to imagine that every observable quantity simply possesses a pre-existing value waiting to be revealed. A measurement of that observable should then uncover the same value regardless of which other compatible quantities happen to be measured alongside it. That is the kind of behaviour we naturally expect from ordinary classical properties. If a suitcase weighs 20 kilograms, its weight does not depend on whether you also measure its colour. Quantum mechanics does not generally permit such a simple assignment. The Koch-Specker theorem shows that, for suitable quantum systems, it is impossible to assign definite values to all relevant observables in advance, while preserving the relationships demanded by quantum theory and making those values independent of the measurement context. The word context is important here. In quantum mechanics, a particular observable may be measured as part of different compatible sets of measurements. A non-contextual hidden value picture would say that the observable carries the same predetermined answer regardless of which compatible set is chosen. The theorem shows that this cannot generally reproduce the structure of quantum mechanics. The measured value therefore cannot always be imagined as a little label permanently attached to the system and merely read by the apparatus. The complete measurement arrangement matters. This does not mean that absolutely no physical properties can exist before measurement. That would be too strong. It means that any deeper theory reproducing quantum mechanics cannot assign ordinary, measurement-independent classical values to every quantum observable in the naive way. Bell's theorem and the Koch-Specker theorem therefore attack two different pieces of classical intuition. Bell shows that definite hidden outcomes cannot generally be combined with the required form of locality. Koch and Specker show that definite values cannot generally be assigned to all observables independently of measurement context. Neither theorem tells physicists which interpretation of quantum mechanics must be accepted, but together they make the landscape much less comfortable. A deeper theory may still exist. It simply cannot look like classical mechanics with a few hidden numbers tucked underneath. If definite outcomes arise from additional variables, those variables may have to be non-local, contextual, or both. If the wavefunction is complete, then the theory must explain how definite records emerge without appealing to an underlying collection of classical properties. And if collapse is fundamental, then the collapse process must still be described with enough precision to distinguish measurement from ordinary interaction. The old escape route was tempting because it promised that quantum uncertainty might be nothing more than ignorance. Bell and contextuality show why that hope cannot survive in its simplest form. The microscopic world does not seem to be carrying around a complete classical answer sheet, waiting politely for an apparatus to read it. Whatever lies beneath quantum measurement, it must be stranger than that. One of the most important developments in the modern understanding of quantum measurement came from recognizing something that is almost impossible to avoid in the real world. Nothing macroscopic is truly isolated. A detector may appear to be sitting quietly on a laboratory bench, but physically it is being disturbed every moment. Air molecules collide with its surface. Photons scatter from it. Thermal radiation is absorbed and emitted. Vibrations pass through the surrounding material. Countless internal particles interact with one another. All of this matters because quantum systems can become entangled with whatever they interact with. The physicist Heinz-Dieter Zeh was among the first to explore the consequences of this idea systematically for the measurement problem. Later, Wojciech Zurek developed the theory much further, helping to establish what is now known as environmental decoherence. The basic idea begins with an ordinary quantum measurement. Suppose a particle is in a superposition of two possible outcomes. It interacts with a detector. The detector then becomes entangled with those alternatives. One part of the combined state contains the particle associated with one result and the apparatus displaying the corresponding reading. Another part contains the other result and its matching apparatus state. But the detector does not remain alone. Almost immediately, its different possible states begin interacting differently with the surrounding environment. If a pointer is in one position, nearby photons scatter from that arrangement. If it is in another position, they scatter slightly differently. Air molecules collide with the two possible configurations in different ways. Thermal radiation leaving the apparatus carries information about its state. The environment therefore becomes entangled with the measurement record as well. The original quantum correlation has now spread outward. Instead of having only a particle correlated with a detector, there may be a particle correlated with a detector, correlated with photons, air molecules, vibrations, and enormous numbers of internal degrees of freedom. The environment quietly begins carrying copies of information about what the apparatus is doing. This has a dramatic effect on quantum interference. For two alternatives to interfere clearly, the relative phase between their quantum amplitudes must remain coherent. That phase relationship is what allows the alternatives to reinforce or cancel one another. But once the system becomes entangled with a complicated environment, the phase information is no longer contained neatly within the system itself. It becomes distributed across vast numbers of environmental correlations. The information has not necessarily been destroyed in the deepest mathematical sense. It has become enormously difficult to access. To observe interference again, an experimenter would have to control not just the detector, but in principle, all the environmental particles that have become correlated with it. For a microscopic system in an exceptionally well-isolated laboratory, that may sometimes be possible. For an ordinary macroscopic object, it rapidly becomes hopeless. The mathematical description of this process often uses something called a reduced density matrix. The full quantum state would include the system together with every relevant part of the environment. That description quickly becomes far too complicated to track directly. Instead, physicists can mathematically ignore the environmental details and ask only what can be observed from the smaller system itself. The reduced density matrix provides that local description. When decoherence has become strong, the mathematical terms responsible for observable interference between macroscopically different alternatives become extremely small. From the viewpoint of someone examining only the apparatus, the system begins to behave almost as though it were an ordinary classical mixture of possible outcomes. This is one of the central achievements of decoherence. It explains why quantum interference, so obvious in carefully isolated particles, becomes almost impossible to observe in everyday objects. Wojciech also developed an important idea known as environment-induced superselection. The name is rather formidable, but the physical idea is manageable. Not every possible quantum state interacts with the environment equally. Certain states are especially robust. These are often called pointer states. Imagine a measuring device whose pointer can rest in different positions. A bizarre superposition of several widely separated pointer positions is extremely fragile because the environment interacts differently with each position and rapidly records information about them. A definite pointer position, by contrast, can remain stable despite continued environmental interaction. The environment therefore effectively selects certain preferred states that are much more resistant to decoherence. These stable states tend to resemble the kinds of definite positions and records familiar from classical physics. That helps explain an important part of the measurement problem. Why do measuring devices settle into recognizable pointer positions rather than arbitrary superpositions of wildly different macroscopic states? environmental interactions favour particular robust states. The surrounding world is, in a sense, constantly monitoring certain physical properties, and it does this with extraordinary speed. For large objects under ordinary conditions, decoherence times can be fantastically shorter than anything a human being could perceive. A visible object in a room is continually struck by enormous numbers of air molecules and photons. Even tiny differences in its position can become encoded into the environment almost immediately. Depending on the size of the object, its temperature, the surrounding gas, and the separation between the alternatives, the suppression of observable interference can occur in fractions of a second so tiny that everyday language barely has any intuitive use for them. This explains why the macroscopic world looks so stubbornly classical. A chair does not visibly interfere with another possible position of itself. A laboratory pointer does not appear blurred between several outcomes. A coffee cup does not normally require a quantum interpretation before anyone is allowed to drink from it. The environment has already interacted with these objects on an overwhelming scale. And importantly, none of this requires consciousness. No human mind needs to look at the detector for decoherence to occur. The scattering photons and air molecules are quite capable of doing the job without supervision. Environmental decoherence, therefore, provides a powerful physical explanation for why macroscopic quantum superpositions become effectively invisible, and why certain stable, approximately classical records emerge. It bridges a large part of the gap between delicate quantum behaviour and the solid-looking world of ordinary experience. But there is one distinction that must remain very clear. Decoherence explains why different macroscopic alternatives cease to interfere for practical purposes. It explains why certain records become stable. It explains why the world begins to look classical. Whether it explains why only one of those records is actually realized is a different question. And that difference is where the measurement problem becomes subtle once again. Decoherence solves an enormous part of the puzzle, but it does not quite solve the part people most want solved. After a quantum system interacts with a measuring device, and that device becomes entangled with the surrounding environment, the interference between different macroscopic outcomes can become effectively impossible to observe. From the perspective of the local apparatus, the alternatives begin to look classical. One pointer position, or another. One detector record, or another. The trouble is that the complete quantum state still contains all of those correlated alternatives. Suppose a particle can produce two possible measurement results. One branch of the state contains the particle associated with the first outcome, the detector showing the first reading, and an environment carrying information about that reading. Another branch contains the second outcome, the second detector reading, and a correspondingly different environmental state. Under ordinary unitary evolution, both correlations remain present in the total wave function. Nothing in the Schrödinger equation has literally erased one of them. The environment has instead made the alternatives practically unable to interfere with one another. This distinction is subtle, but it matters enormously. To understand why, it helps to compare two different kinds of statistical description. Imagine an ordinary classical coin hidden beneath a cup. The coin is definitely heads or definitely tails. You simply do not know which. If you assign equal probabilities to the two possibilities, those probabilities describe your ignorance about one underlying reality. Physicists would call that a proper mixture. One outcome has actually occurred. The uncertainty exists because information is missing. Now consider a quantum system that has become entangled with its environment. If you ignore the enormous number of environmental details and calculate only what can be observed locally, The resulting description may look very similar to a classical probability distribution. This local description is represented mathematically by the reduced density matrix. After strong decoherence, the interference terms between different macroscopic alternatives become extremely small. The reduced state can then look, for almost every practical measurement, as though the apparatus simply has one definite outcome or another with ordinary classical probabilities. But the origin of those probabilities is different. The complete system has not necessarily chosen one alternative. Instead, the apparatus is entangled with environmental states that are no longer being tracked. This is often called an improper mixture. The name is not intended to suggest that anything has gone wrong. It means that the apparent mixture arises from entanglement with degrees of freedom that have been ignored, rather than from ordinary ignorance about one already selected classical state. Locally, the two situations can produce the same observable statistics. Globally, they are not the same physical description. That is why decoherence cannot simply be renamed collapse. The reduced state may behave exactly as though collapse had occurred for all realistic local predictions, but the total wave function can still contain every correlated alternative. This is where decoherence achieves something very important without achieving everything. One major part of the measurement problem concerns why certain outcomes appear stable and preferred. A measuring apparatus could, mathematically, be represented in many different combinations of states. Yet in ordinary life, we see robust pointer positions, stable detector readings, and persistent records. Environmental decoherence provides a powerful explanation for this. Certain states interact with the environment in a way that allows them to remain stable. These are the pointer states associated with environment-induced superselection. A definite position of a macroscopic pointer is usually far more robust than a delicate superposition of widely separated positions. The environment therefore helps identify the basis in which classical-looking records naturally emerge. This addresses much of what is called the preferred basis problem. It explains why the world does not appear to settle into arbitrary combinations of bizarre macroscopic states. Instead, certain physically stable configurations are continually reinforced by environmental interaction. But the definite outcome problem remains. Why does one of those stable alternatives become the single outcome that is actually experienced? Decoherence on its own does not answer that question. The difference becomes even clearer if we think about reversing the process. When information about a quantum system spreads into the environment, recovering the original interference would require regaining control over the correlations that have been dispersed. For a very small and carefully isolated system, experimental techniques can sometimes reverse forms of decoherence or produce recoherence. That is possible because the relevant environment can be limited and controlled. For a macroscopic object, the situation is completely different. The information may have leaked into vast numbers of photons, air molecules, internal vibrations, and thermal degrees of freedom. To reconstruct the original coherence, one would need to manipulate an astronomical number of microscopic details with extraordinary precision. In practice, that is hopeless. The process is effectively irreversible. But effective irreversibility is not the same thing as fundamental destruction. A glass shattering on the floor is also effectively irreversible in everyday life. In principle, the microscopic laws do not necessarily forbid every molecule from returning to its earlier position. The reversal is simply so fantastically improbable and difficult to control that it never happens in ordinary experience. Decoherence has a similar character. The interference information becomes dispersed so widely that no realistic observer can retrieve it. But under unitary quantum mechanics, that information is not automatically annihilated. This matters because practical impossibility does not, by itself, explain unique reality. If all alternatives remain in the global state, then something else must account for why only one appears to be actual. Different interpretations take different routes. One possibility is to accept that all decohered alternatives continue to exist. That is the broad strategy of Everettian or many worlds approaches. Another is to introduce additional variables that identify one actual configuration while the wave function continues evolving. That is the path taken by Bohmian mechanics. A third option is to change the dynamics themselves so that superpositions physically collapse when certain conditions are reached. Objective collapse theories follow this route. Other interpretations instead reconsider what the wave function means, what counts as a fact, or whether quantum states should be treated as observer-independent physical objects at all. These are not minor philosophical decorations. They are responses to the exact gap left by decoherence. Decoherence explains why the alternatives stop visibly interfering. It explains why certain records become stable. It explains why classical behaviour emerges with astonishing effectiveness from quantum interactions. What it does not independently explain is why one possibility becomes the only result we experience. The alternatives may become silent to one another. They may become practically inaccessible. They may behave like separate classical possibilities. But silence is not the same as disappearance. And somewhere between those two ideas lies the unresolved heart of the measurement problem. One of the boldest responses to the measurement problem is also, in a strange way, one of the simplest. Do not add collapse at all. In 1957, the American physicist Hugh Everett III proposed what he called the relative state formulation of quantum mechanics. His idea was to take the ordinary unitary evolution of the wave function seriously and apply it universally, not just to electrons, not just to photons, but to measuring devices, laboratories, observers, and ultimately the universe as a whole. In this picture, the Schrödinger equation never suddenly gives way to a different rule during measurement. There is no special boundary where the quantum description stops. There is no physical collapse inserted when a detector clicks. Everything continues evolving according to the same underlying quantum dynamics. Suppose a particle is in a superposition of two possible spin outcomes. A measuring device interacts with it. Under ordinary unitary evolution, the particle and apparatus become entangled. One component of the total state contains the particle associated with upward spin and the apparatus displaying upward. Another contains downward spin and the apparatus displaying downward. Now include the observer. The observer looks at the apparatus. Again, the interaction can be treated quantum mechanically. One component now contains an observer who has seen upward. Another contains an observer who has seen downward. The key point is that each version of the observer has a perfectly definite record relative to the corresponding component of the total state. The observer associated with the upward result does not see a vague blur containing upward and downward at the same time. That observer has a memory of seeing upward. The observer correlated with the downward result has a memory of seeing downward. Each record is internally definite. The superposition exists in the larger quantum description connecting those different correlated alternatives. This is the central idea behind what later became popularly known as the many worlds interpretation. That phrase can make the theory sound more dramatic than the mathematics requires. It can suggest that every measurement triggers some mysterious machine that creates entirely new universes from nothing. That is not the essential claim. The central claim is much more restrained, even if its consequences are enormous. The universal quantum state simply continues evolving. As interactions spread information through the environment, different components of that state become effectively independent. These components are often described as branches. Environmental decoherence helps explain why those branches behave as though they are separate classical histories. Imagine again that a detector records two possible outcomes. Each outcome becomes correlated with enormous numbers of surrounding particles. Photons scatter differently. Air molecules respond differently. Computer memories store different information. The observer forms different memories. As those environmental correlations multiply, interference between the different macroscopic records becomes fantastically difficult to observe. The branches effectively stop interacting in any ordinary practical sense. This gives the Everettian picture something it badly needs. Without decoherence, it would be difficult to explain why the universal wavefunction should naturally divide into anything resembling stable classical worlds. With decoherence, certain robust patterns emerge. A detector showing upward belongs to one approximately autonomous branch. A detector showing downward belongs to another. Each contains a consistent record of what happened. The branching is not necessarily perfectly sharp. There is no obvious universal instant when one world becomes exactly two worlds. Decoherence is a continuous physical process, and the boundaries between branches are approximate. That is why many physicists prefer to think of branching as an emergent structure rather than as a fundamental process written separately into the laws. The attraction of the Everettian approach is clear. It removes one of the most awkward elements of textbook quantum mechanics. There is no need to explain when collapse happens, because collapse never happens. There is no need to identify a special measurement boundary. A detector is treated quantum mechanically. An observer is treated quantum mechanically. The environment is treated quantum mechanically. The same equations apply throughout. But removing collapse creates a new difficulty. Probability becomes harder to understand. If every allowed outcome occurs in some branch of the universal wavefunction, what does it mean to say that one outcome has a probability of 1/2 and another has a probability of 1/10? Before a measurement, an observer knows that different future versions of that observer will become correlated with different results. If all those outcomes occur, why should the observer expect them with frequencies given by the Born rule? The obvious temptation is to count branches. But branch counting does not work cleanly. There is no unique fundamental number of branches. Decoherence can continually produce increasingly fine-grained distinctions, and the branching structure is approximate rather than a neat collection of equally weighted universes. The Born rule instead assigns importance according to the squared magnitude of quantum amplitudes. Everettian approaches therefore need to explain why rational expectation and observed frequency should follow those amplitude weights. Several arguments have been developed. Some appeal to decision theory. Others use symmetry, typicality, or properties of the quantum state. Physicists and philosophers continue to debate how successful these derivations are, and whether probability has been fully explained when every possible outcome remains in the theory. This reveals the peculiar trade being offered. Traditional collapse-based quantum mechanics keeps one outcome, but introduces a special process whose exact physical trigger is difficult to define. Everett removes that process entirely. The Schrödinger equation remains untouched. But the price is accepting that the universal wavefunction contains a vast collection of decohered alternatives, all continuing as parts of the total quantum state. Exactly what these branches should be regarded as remains debated. Are they literally separate worlds? Emergent histories, patterns within one universal wave function? Different physicists describe the ontology in different ways. What they share is the rejection of fundamental collapse. The attraction is theoretical economy. One universal state. One form of evolution. No special intervention during measurement. The cost is that the familiar idea of one unique unfolding history of the universe is no longer fundamental. The measurement problem has not disappeared. It has been transformed. Instead of asking why many possibilities collapse into one result, the question becomes why an observer finds a definite result within one branch, why those branches take on approximately classical structure, and why their experiences follow the probabilities predicted by the Born rule. Hugh Everett III preserved the quantum equations by refusing to make possibility disappear. The price was allowing every permitted alternative to remain somewhere inside the evolving quantum state. Another way to respond to the measurement problem is to keep one definite physical reality while allowing the wave function to continue evolving. This is the route taken by de Broglie, Born theory, also known as Bohmian mechanics. Its roots go back to the French physicist Louis de Broglie, who proposed a pilot wave picture during the early development of quantum mechanics. Decades later, in 1952, the American physicist David Bohm developed a much more complete hidden variable formulation built around a similar idea. The central claim is strikingly simple. Particles always have definite positions. An electron is somewhere. A photon, where the formulation applies through an appropriate particle description, is associated with an actual configuration. A measuring device has a definite physical arrangement. There is no need to say that all of these objects literally lack positions until somebody looks at them. The wave function still exists, and it still evolves according to the Schrödinger equation. But in Bohmian mechanics, the wave function does something more than merely encode probabilities. It guides the motion of the actual particle configuration. The particles follow definite trajectories, while the wave function influences how those trajectories develop through what is known as the guiding equation. This produces a very different picture of quantum reality from the textbook collapse story. Consider the double slit experiment. A particle approaches a barrier containing two openings. In ordinary quantum mechanics, the wave function passes through both available paths, and the amplitudes associated with those paths interfere. In Bohmian mechanics, the wave function still passes through both slits, but the particle itself follows one actual trajectory. It goes through one slit, not both. The wave function travelling through the full experimental arrangement then guides the later motion of the particle. The interference structure created by the wave function shapes the distribution of possible trajectories. Send one particle at a time, and each particle arrives at one definite location on the screen. Repeat the experiment many times, and the collection of impacts forms the familiar interference pattern. This gives Bohmian mechanics an appealing kind of visual clarity. The particle is never literally smeared across the detector. It occupies one actual position. The wave function remains extended and influences how the particle moves. The measurement problem can then be approached in a similarly concrete way. Imagine measuring the spin of a particle. The interaction causes the wave function of the combined particle and apparatus to separate into different branches. One branch corresponds to an apparatus displaying one result. Another corresponds to a different pointer position. Under ordinary unitary evolution, both branches remain part of the wave function, but the actual configuration of all the particles making up the system and apparatus lies in only one of them. If the configuration enters the branch corresponding to an upward result, then the detector physically records upward. The particles making up the pointer occupy the upward position. The computer stores the upward result. The observer's physical configuration becomes correlated with that record. There is therefore one actual outcome. The other branches of the wave function do not necessarily disappear. They remain mathematically present. These are sometimes informally called empty waves or empty branches because they no longer contain the actual configuration of the particles. This creates what is known as effective collapse. The universal wave function has not fundamentally collapsed. Instead, its branches have separated in such a way that the occupied branch can evolve largely independently of the empty ones. For practical purposes, the observer can then use the occupied branch almost as though the wave function had collapsed in the ordinary textbook sense. The result is definite without requiring a special physical event triggered by measurement. Measurement becomes an ordinary interaction. The apparatus does not need a mysterious exemption from quantum mechanics. It simply becomes entangled with the system, while the actual particle configuration ends up associated with one possible record. This seems to solve one of the hardest parts of the measurement problem. There is one real configuration. There is one actual pointer position. There is one outcome experienced by the observer. But a new question immediately appears. Where do the familiar quantum probabilities come from? Bohmian mechanics introduces an important idea known as quantum equilibrium. If the possible configurations of particles are distributed according to the squared magnitude of the wave function, then the statistical predictions of Bohmian mechanics reproduce the Born rule. In other words, repeated experiments produce the same probability distributions observed in ordinary quantum mechanics. This is crucial because Bohmian mechanics would not be empirically successful if it predicted different detector frequencies in experiments that quantum theory already describes correctly. The deeper issue concerns why quantum equilibrium should hold. Different accounts appeal to ideas such as typicality, dynamical behaviour, or equilibrium like reasoning to explain why observers should expect configurations distributed in this way. The status of that explanation remains an important foundational question. And there is another price. Bohmian mechanics is explicitly non-local. For a system containing several entangled particles, the velocity of one particle can depend on the configuration of distant particles through the shared wave function. That does not provide a simple method for sending controllable messages faster than light, so it does not automatically produce operational conflict with relativity. But it does mean that the underlying ontology is not local in the familiar classical sense. This feature connects directly with John Stuart Bell's theorem. Bell showed that no theory reproducing all quantum predictions can preserve the relevant combination of local causation and predetermined outcomes. Bohmian mechanics keeps definite particle configurations. It therefore gives up locality. This is an important reminder that hidden variable theories do not restore the comfortable classical universe many people initially imagine. The particles may have positions, but the rules connecting those positions can involve the entire configuration of an entangled system. The theory is deterministic at its fundamental level, yet observed outcomes still follow quantum probabilities because the exact initial configuration is generally inaccessible. It provides definite results without fundamental collapse, but only by accepting a profoundly non-local underlying structure. That is the trade. Hugh Everett III kept only the wave function and allowed all branches to remain. Louis de Broglie and David Bohm kept the wave function too, but added one actual configuration moving through it. The measurement apparatus can still enter a superposition within the wave function. The difference is that reality does not occupy every part of that superposition in the same way. One configuration is actual. One pointer physically points somewhere. One record is made. The measurement problem can therefore be softened without making the wave function disappear. But the price of keeping one definite world is accepting that its hidden machinery is far less local and far less classically familiar than the world first appears. One way to solve the measurement problem is to stop treating collapse as a vague special event and instead make it part of the actual laws of physics. This is the basic idea behind objective collapse theories. Rather than saying that the wave function suddenly changes because a measurement has taken place, these theories propose that quantum states can genuinely collapse through a physical process governed by new mathematical rules. The collapse is not caused by a conscious observer. It does not wait for someone to look, and it does not depend on drawing an arbitrary boundary between a microscopic system and a macroscopic apparatus. Instead, the dynamics themselves are changed. One of the best-known examples was introduced in 1986 by the physicists Giancarlo Girardi, Alberto Rimini, and Tullio Weber. Their model begins with the ordinary quantum wave function, evolving according to the Schrödinger equation. But it adds rare, spontaneous localization events. A microscopic constituent has a very small probability of suddenly becoming much more localized in space. For a single particle, this happens extraordinarily rarely. In the original version of the model, the typical waiting time for one isolated constituent is on the order of hundreds of millions of years. That means an individual atom can behave almost exactly as ordinary quantum mechanics predicts for immensely long periods. Its wave function can spread, it can interfere, it can remain in superposition. But the situation changes dramatically when huge numbers of particles become linked together inside a macroscopic object. A measuring device contains an enormous number of microscopic constituents. A pointer, a grain of dust, or even a tiny visible object contains vastly more particles than any isolated laboratory quantum system. Each constituent has its own tiny chance of localizing. When the states of those particles are correlated, a localization affecting one part of the object can effectively localize the larger combined state. This creates what is known as the amplification mechanism. The more constituents an object contains, the greater the overall rate at which localization becomes important. A lone microscopic particle may wait an unimaginably long time. A macroscopic object containing roughly Avogadro scale numbers of constituents experiences effective localization enormously more quickly. This gives the theory a natural distinction between microscopic and macroscopic behaviour, without needing to declare that detectors somehow belong to a different category of matter. The original Girardi, Rimini, and Weber model also introduced a characteristic localization width of roughly 1/10,000,000th of a meter. That is about 100 nanometers. The localization is therefore not a perfect mathematical point. Instead, the wave function is sharply concentrated over a small spatial region. For microscopic systems, these occasional localization events barely disturb the usual predictions of quantum mechanics. For sufficiently large systems, they continually suppress superpositions involving very different macroscopic positions. A pointer therefore does not remain indefinitely in a superposition of pointing left and pointing right. The modified dynamics drive the state toward a definite macroscopic configuration. Measurement becomes less mysterious because the detector is simply another physical object subject to the same collapse law. No special act of observation is required. Later developments refined this general idea. One particularly important approach is continuous spontaneous localization, Instead of imagining collapse as a sequence of occasional sudden jumps, continuous spontaneous localization modifies the evolution more smoothly through an ongoing random process. The physicist Philip Pearl played a major role in developing this kind of model. The wave function still experiences stochastic, meaning fundamentally random, changes, but the localization occurs continuously rather than through isolated discrete events. Again, the effects are designed to be extremely small for microscopic systems, while becoming increasingly important as mass and complexity grow. The aim is to preserve the overwhelming experimental success of ordinary quantum mechanics at small scales, while naturally producing definite macroscopic outcomes. Other proposals have suggested that gravity itself might somehow be involved. The physicist Lajos Dissi developed models in which gravitational effects contribute to the instability of spatial superpositions. Roger Penrose independently argued that a superposition involving substantially different distributions of mass may correspond to incompatible spacetime geometries. In Penrose's proposal, that mismatch could make sufficiently large superpositions unstable. The larger the gravitational difference between the alternatives, the shorter the expected lifetime of the superposition. This possibility is particularly intriguing because the measurement problem sits at the boundary between quantum theory and the classical world, while gravity remains the major fundamental interaction that has not yet been fully reconciled with quantum mechanics. But these gravitational collapse ideas remain proposals. There is no universally accepted theory demonstrating that gravity causes wave function collapse, and no experiment has established such a mechanism as part of nature. That leads to one of the great advantages of objective collapse theories. They can, at least in principle, be experimentally distinguished from ordinary quantum mechanics. Most interpretations preserve the standard equations and therefore predict exactly the same laboratory statistics. Objective collapse models do something different. They modify the dynamics. That means they can produce small but real physical effects. A collapse process may introduce tiny amounts of energy into a system. It may create slight spontaneous heating. Some models can predict weak forms of radiation, others can produce additional random motion, or cause quantum interference to disappear slightly faster than ordinary environmental decoherence would predict. These effects are expected to be extremely small. If they were large, they would already have been noticed. But increasingly sensitive experiments can search for them. Matter wave interferometers test whether larger and heavier objects continue to maintain quantum coherence. Mechanical resonators can look for unexplained noise or motion. Highly sensitive precision experiments can search for excess heating. Levitated particles, isolated from many ordinary environmental disturbances, provide another promising way to test whether quantum superpositions decay faster than standard theory predicts. The logic is elegant. If the collapse parameters are too strong, experiments should already have revealed deviations from ordinary quantum mechanics. Because those deviations have not been observed, increasingly large regions of possible parameter space can be ruled out. Objective collapse models therefore turn at least part of the measurement problem into experimental physics. They make a clear proposal. Superpositions do not survive forever. Macroscopic definiteness is not merely apparent. Wave functions genuinely localess, and they do so because the laws governing quantum evolution contain a small amount of fundamental randomness that becomes overwhelmingly important for large systems. The price is equally clear. The Schrödinger equation can no longer be the complete law of quantum evolution. Something new must be added. That addition must reproduce every successful quantum experiment already performed, while also explaining why the macroscopic world remains definite. It must avoid producing too much unwanted heat, radiation, or noise. And it must eventually survive direct experimental tests. The attraction of objective collapse is that it refuses to hide the measurement problem inside the word measurement. Instead, it makes a bold claim. If nature truly chooses one outcome, then perhaps the equations themselves should say exactly how that choice occurs. Some approaches to the measurement problem begin from a very different suspicion. Perhaps the difficulty does not come from a missing physical mechanism at all. Perhaps it comes from assuming that quantum theory must describe reality in the same way classical physics once seemed to. Instead of adding hidden particles, multiplying branches, or modifying the Schrödinger equation, these approaches ask whether ideas such as a universal quantum state, an observer-independent set of properties, or one all-encompassing description of events are themselves part of the problem. One influential example is relational quantum mechanics, developed by the physicist Carlo Rovelli. Its central proposal is that physical quantities do not necessarily possess absolute values that exist independently of every other system. Instead, values become definite relative to physical interactions. This does not mean that reality is created by human opinion. The word relational refers to relationships between physical systems. An electron can interact with a detector. A detector can interact with another apparatus. A person can later interact with the detector by reading its result. None of these systems needs consciousness in order for the interaction to matter. In relational quantum mechanics, every physical system is treated on the same footing. There is no fundamental division between observer and observed. A measuring device is simply one physical system interacting with another. Suppose a detector measures the spin of a particle. Relative to the detector, a definite result may be established through that interaction. But another system that has not yet interacted with the detector may still use a quantum description containing several possibilities. The two descriptions are not necessarily regarded as contradictory because they refer to facts relative to different physical systems. Once the systems interact and compare records, new correlations are established. This shifts the meaning of the measurement problem. Instead of asking when one universal wavefunction collapses for the entire universe at once, relational quantum mechanics asks which physical quantities have become definite relative to which systems. The cost is that the familiar idea of one complete catalogue of properties existing simultaneously from a view outside the universe is no longer fundamental. A rather different approach appears in quantum Bayesianism, associated especially with Christopher Fuchs, Erdiger Schack, and Nathaniel David Mermin. Here the quantum state is not treated as a literal physical object spread through the world. It represents an individual agent's expectations about the possible consequences of actions performed on physical systems. Quantum probabilities are therefore understood as personal probability assignments, constrained by the mathematical structure of quantum theory. The word personal needs some care. It does not mean arbitrary. An agent cannot assign probabilities however they please and still expect those expectations to survive contact with experiment. The rules of quantum mechanics impose powerful consistency requirements, but the quantum state itself belongs to the agent's description rather than existing as a unique physical object independently of every possible user of the theory. This radically changes the meaning of collapse. Suppose an observer assigns probabilities to several possible detector results. The experiment is performed. One result is experienced. The observer then updates the quantum state. From the quantum Bayesian perspective, there is no need to imagine a physical wave suddenly contracting across space. The state changes because the agent's expectations have changed after acquiring new experience. Collapse becomes a form of probability updating. The world still matters. The experience was not chosen by the observer, but the wave function is not required to be a material entity that physically jumps whenever information is obtained. This avoids the problem of locating a mysterious collapse mechanism. It also raises deeper philosophical questions about how much of quantum theory describes the external world directly, and how much describes an agent's expectations about interactions with it. Another attempt to reformulate the problem comes from the consistent histories approach. This framework was developed through the work of physicists, including Robert Griffiths, Roland Ohms, Murray Gell-Mann, and James Hartle. Rather than concentrating only on measurements made at one instant, consistent histories considers entire sequences of possible quantum events through time. A history might describe a particle occupying one region, later passing through another region, and eventually producing a particular detector record. Quantum mechanics can assign probabilities to such histories, but not every arbitrary collection of possible histories can be treated as an ordinary set of mutually exclusive alternatives. The histories must satisfy a consistency condition. Closely related formulations use decoherence conditions to ensure that interference between the alternatives is sufficiently absent for ordinary probabilistic reasoning to work. When that condition is satisfied, probabilities can be assigned to the different possible histories in a mathematically consistent way. This creates a framework in which macroscopic records and classical-looking sequences of events can emerge without requiring an external observer to collapse the wave function. But consistent histories includes an important restriction. Different valid frameworks cannot always be freely combined. Imagine that one framework describes a quantum system using one particular set of properties, while another valid framework uses a different, incompatible set. Classical intuition encourages us to gather every statement together and build one grand story containing all of them. Quantum mechanics may not allow that. The single framework rule says that reasoning must remain within one compatible framework at a time. Statements taken from incompatible frameworks cannot simply be merged as though they described one ordinary classical history. A loose analogy would be trying to combine two maps that use fundamentally different coordinate systems without first checking whether their features can meaningfully be compared. Each map may be useful. The mistake comes from assuming that every feature can automatically be placed onto one common picture. Relational quantum mechanics. Quantum Bayesianism and consistent histories therefore share an interesting strategy, even though they disagree strongly about what quantum theory means. None requires the familiar textbook image of a universal wave function physically collapsing because a human observer looks at an apparatus. Relational quantum mechanics revises the idea of absolute physical facts. Quantum Bayesianism revises the meaning of the quantum state and probability. Consistent histories revises the assumption that every valid quantum description can be combined into one universal classical narrative. Each approach tries to remove some of the tension by questioning assumptions that seemed obvious before quantum mechanics arrived. That can make them feel less dramatic than theories proposing new particles or spontaneous collapse. But conceptually, they are every bit as radical. They suggest that perhaps the measurement problem persists because physics keeps asking quantum theory to provide something nature never promised. One perfectly objective quantum state. One set of properties valid from every perspective. One universal history into which every possible statement can be inserted. Remove those assumptions, and parts of the problem begin to look different. Whether they disappear completely is another matter. The equations may remain unchanged. but the meaning of a fact, a probability, an observer, and even a physical state can shift beneath them. And sometimes the most radical way to solve a problem is not to change the mathematics at all. It is to reconsider what we thought the mathematics had been describing. The measurement problem is difficult to test experimentally for a rather frustrating reason. Many of the leading interpretations of quantum mechanics predict exactly the same results in ordinary experiments. An Everettian physicist may describe a measurement as branching. A Bohmian physicist may describe one actual particle configuration guided by the wavefunction. Another researcher may regard collapse as an update in information. Yet when they calculate where a photon should appear on a detector, they can arrive at precisely the same probabilities. Their stories about reality may be radically different, while their laboratory predictions remain identical. That makes experimental discrimination unusually difficult. There is, however, another way to attack the problem. Instead of asking which interpretation sounds most convincing, physicists can search for the point where ordinary quantum mechanics might stop working. If superposition is genuinely universal, then increasing an object's size should not suddenly make quantum behaviour disappear because of size alone. Large objects are certainly harder to isolate. They decohere rapidly because they interact with their surroundings. But that is different from a fundamental law saying that an object becomes too large to exist in a superposition. Matter-wave interferometry provides one of the cleanest ways to investigate this boundary. The idea reaches back to Louis de Broglie's proposal that matter possesses wave-like properties. Send a suitable object through an interferometer, maintain enough coherence between different possible paths, and the resulting detection pattern can reveal interference. Interference is important because ordinary classical particles following independent alternatives do not naturally produce the same pattern. The experiment therefore tests whether the centre of mass of an increasingly complicated object can still behave according to the quantum superposition principle. The challenge becomes enormous as the object grows. Large molecules contain many atoms that can vibrate and rotate. They emit thermal radiation. They collide with stray gas molecules. Even a single uncontrolled interaction may reveal information about the path and weaken the interference pattern. So maintaining coherence requires extremely careful control of temperature, vacuum conditions, velocity, and environmental disturbance. Researchers at the University of Vienna have spent years pushing these experiments toward larger masses. In 2019, Yakov Fine, Marcus Arndt, Stefan Gerlich, and their collaborators reported interference using large organic molecules containing as many as roughly 2,000 atoms. Their heaviest molecules exceeded 25,000 daltons in mass. They passed through a 2-meter-long interferometer, and the resulting interference fringes agreed closely with quantum predictions. Remarkably, the de Broglie wavelengths associated with the molecules were tens of femtometers, far smaller than the molecules themselves, yet their centre of mass still displayed wave-like interference. 25,000 daltons is still extraordinarily small compared with something we could hold in a hand, but it is vastly more complicated than the single electrons and photons commonly used to introduce quantum mechanics. Each molecule contains thousands of interacting atomic components and many internal modes of motion. And yet the experiment did not reveal a sudden boundary where superposition simply stopped. The quantum rules continued to work. Then, in 2026, the boundary was pushed dramatically farther. Sebastian Pedolino, Bruno Ramrez Galindo, Richard Ferstel, Klaus Hornberger, Marcus Arndt, Stefan Gerlich, and their collaborators demonstrated matter-wave interference using sodium nanoparticles. These were not merely complicated organic molecules, they were tiny pieces of metal containing more than 7,000 atoms and reaching masses greater than 170,000 daltons. The centre of mass of the clusters became delocalized across distances more than an order of magnitude larger than the diameter of the particles themselves. In one reported configuration, the spatial separation reached roughly 133 nanometers. Despite their size and complexity, the sodium clusters still produced interference consistent with ordinary quantum mechanics. The researchers described the experiment as creating a form of Schrödinger cat state, although there was thankfully considerably less fur involved. The comparison refers to the fact that one comparatively large object was placed into a coherent quantum state associated with classically distinct trajectories. The experiment achieved a quantum macroscopicity measure of about 15.5, substantially extending the scale reached by previous matter wave tests. Results like these matter directly to the measurement problem. Objective collapse theories propose that ordinary quantum evolution eventually fails. Depending on the model, increasing mass, particle number, spatial separation, or time spent in superposition can make collapse increasingly likely. If such a process exists, sufficiently ambitious interference experiments could begin to reveal it. Instead of producing the interference predicted by the Schrödinger equation, the superposition would lose coherence even after every known environmental source of decoherence had been carefully accounted for. The 2026 sodium experiment found no such breakdown at the scales it tested. Its results therefore placed stronger restrictions on broad families of proposed modifications in which sufficiently macroscopic superpositions are dynamically suppressed. That does not prove that collapse never occurs. An experiment can test only the range of masses, distances, times, and environmental conditions it actually reaches. A modified theory might predict effects at scales that remain beyond present technology. The lesson is more restrained, but still significant. Every time researchers create a larger coherent superposition and ordinary quantum mechanics continues working, the unexplored territory in which a new collapse mechanism might hide becomes smaller. Other experiments approach the measurement problem from a completely different direction. Instead of making objects heavier, they investigate what happens when observers themselves are included in quantum reasoning. Daniela Froschiger and Renato Renner developed a particularly influential extension of Eugene Wigner's friend thought experiment. Their argument considered several agents using quantum mechanics to reason about measurements performed by one another. Under a particular collection of assumptions, including single outcomes and consistency between the agent's conclusions, the reasoning produces incompatible statements. The significance of the argument remains debated because different interpretations reject or reformulate different assumptions. It nevertheless demonstrates how uncomfortable quantum theory can become when the observer is no longer treated as standing safely outside the mathematics. Experimental physicists have begun exploring simplified versions of these ideas. In 2019, Massimiliano Prietti, Alessandro Fedrizzi, and their collaborators constructed an extended Wigner's friend-style experiment using 6 photons. Quantum degrees of freedom played the roles assigned to observers and their measured systems. The experiment violated the relevant Bell-type inequality by about 5 standard deviations under the assumptions used in the analysis. That result is fascinating, but it must be interpreted carefully. No conscious scientist was placed into a coherent superposition. Nobody built a sealed laboratory containing a physicist who both saw and did not see a measurement result. The so-called observers were small quantum systems acting as simplified physical records. The experiment tested the mathematical structure behind an extended observer scenario, not the experience of a human mind in 2 branches of reality. A related advance came from Kok Wei Bong, Howard Wiseman, and their collaborators. They developed a stronger no-go theorem based on two separated entangled versions of Wigner's friend. Their analysis showed that if quantum evolution can be controlled at the scale of an observer, then a particular combination of assumptions involving locality, freedom from superdeterministic constraints, and absolute observer-independent events cannot all remain true. They also demonstrated the relevant quantum violation in a proof-of-principle experiment where the path of a photon served as the simplified observer. These experiments should therefore not be advertised as proof that reality literally splits, that facts are purely subjective, or that human consciousness obeys some newly discovered quantum rule. The conclusions depend on carefully stated assumptions. Different interpretations escape the contradictions in different ways. What the experiments do show is that ideas once confined almost entirely to thought experiments can increasingly be translated into precise laboratory tests. And beneath all of this lies decoherence. Decoherence itself is not hypothetical. Quantum interference can be deliberately weakened by allowing a system to interact more strongly with its environment. And coherence can be protected by improving isolation. The remarkable difficulty of creating interference with large objects is not evidence that quantum mechanics has failed. Much of that difficulty follows exactly from the enormous number of environmental interactions that increasingly large systems experience. Matter-wave experiments succeed by suppressing those interactions enough for the underlying quantum behaviour to remain visible. So the quantum classical boundary is beginning to look less like a simple border marked microscopic on one side and classical on the other. Instead, increasingly large systems continue to show quantum behaviour when they are isolated and controlled carefully enough. The 2019 molecular experiments pushed coherent matter waves beyond 25,000 daltons and roughly 2,000 atoms. The 2026 sodium experiments pushed matter wave interference beyond 7,000 atoms and 170,000 daltons. Extended Wigner's friend experiments have meanwhile begun probing which combinations of seemingly reasonable assumptions about observers, locality, and objective events can survive the structure of quantum theory. None of this has produced a universally accepted answer to the measurement problem. No experiment has identified a single moment when possibility demonstrably becomes one objective fact. No observed mass threshold has yet shown ordinary quantum mechanics suddenly breaking down, and no laboratory test has forced physicists to agree on whether the wavefunction collapses, branches, guides hidden configurations, or represents something other than a literal physical object. But the problem is no longer confined to philosophical discussion. The experiments are getting larger. The isolation is improving. The tests of modified quantum dynamics are becoming stricter. And thought experiments once involving imaginary friends and unfortunate imaginary cats are slowly being translated into arrangements of photons, molecules, and nanoparticles that can actually be built. The measurement problem remains unresolved, but the boundary around it is being squeezed by experiment, one interference fringe at a time. The quantum measurement problem is sometimes called one of physics' great embarrassments, not because quantum mechanics has failed, quite the opposite. The theory has survived experiment after experiment with extraordinary success. It explains atomic spectra, chemical bonding, semiconductor electronics, lasers, superconducting effects, quantum optics, and the behaviour of particles at scales far beyond direct human intuition. Its predictions are among the most accurate ever produced by science. And yet, sitting quietly beneath that success, there remains a question that physicists still do not answer in one universally accepted way. How does a collection of quantum possibilities become one definite recorded event? Classical physics made measurement feel comparatively simple. an object possessed properties. A measuring device discovered them. If the position of a planet was unknown, the planet still had a position. If the temperature of a gas was uncertain, the molecules were still assumed to possess definite microscopic states. Probability usually represented ignorance. Quantum mechanics changed that picture. The quantum state, often represented by a wavefunction, does not merely catalogue values that are secretly waiting to be uncovered. It contains amplitudes associated with different possible outcomes. Those amplitudes can interfere. A particle can occupy a superposition associated with several alternatives, and when that state is isolated, it evolves according to the Schrödinger equation. That evolution is smooth, it is deterministic. It preserves the coherent relationships between the different components of the quantum state. Then measurement enters. Instead of several possible results being visible at once, a detector produces one outcome. One pixel lights, one pointer settles, one spin value appears. The Born rule tells physicists how likely each result is to occur. It has proven spectacularly reliable, but calculating probabilities and explaining the physical appearance of one actual outcome are not the same thing. Textbook quantum mechanics traditionally bridges that gap with wavefunction collapse. Before measurement, several alternatives are present. After measurement, the state associated with the observed result remains. But this introduces a second kind of evolution. The Schrödinger equation produces continuous and deterministic change. Collapse is probabilistic and in its idealized textbook form discontinuous. One law preserves the superposition. Another seems to remove it. John von Neumann's measurement chain makes the tension especially clear. A particle interacts with a detector. The detector interacts with a computer. The computer produces a record. That record reaches an observer. If each physical system is itself described quantum mechanically, then the correlations can simply continue spreading outward. Moving the boundary between quantum system and classical apparatus does not automatically explain why collapse should occur at one particular point. Environmental decoherence provides one of the most important pieces of the modern answer. Heinz-Dieter Zeh and Wojciech Zurek helped show how interactions with the environment rapidly destroy observable interference between macroscopically different alternatives. Air molecules collide with an apparatus. Photons scatter from it. Thermal radiation escapes. Information about the different possible records becomes distributed into countless environmental degrees of freedom. Certain robust pointer states survive this environmental monitoring much better than delicate superpositions. The result is an approximately classical world filled with stable records. Decoherence, therefore, explains a great deal. It explains why macroscopic superpositions are so difficult to observe. It helps explain why certain measurement outcomes form the preferred basis of familiar experience. It explains why ordinary objects appear classical without requiring a conscious mind to force them into definiteness. But decoherence does not by itself select one uniquely actual result. Under ordinary unitary evolution, the full quantum state can still retain all of the decohered alternatives. They may no longer interfere in practice. They may become effectively isolated from one another. But losing observable interference is not automatically the same as explaining why only one result exists. That remaining gap is where interpretations begin to separate. Hugh Everett III removes collapse entirely. The universal wavefunction continues evolving, and the different decohered outcomes persist as branches, each containing a definite record relative to that branch. Bohmian mechanics takes another route. The wavefunction remains, but one actual configuration of particles exists within it, giving the world definite positions and definite measurement records. Objective collapse theories make a more direct modification. They alter quantum dynamics so that sufficiently large or complicated superpositions physically localize, turning collapse into a genuine stochastic process rather than an undefined response to observation. Other approaches challenge the assumptions behind the problem itself. Relational quantum mechanics treats physical values as relative to interactions between systems. Quantum Bayesianism interprets the quantum state as an agent's probability assignments rather than a literal physical object. Consistent histories restricts which sets of quantum descriptions can meaningfully be combined into one account. These are not merely philosophical decorations added after the real physics is finished. They disagree about what exists. They disagree about what the wavefunction represents. They disagree about whether probability is fundamental, whether collapse is physical, whether all outcomes continue to exist, and whether there is one observer-independent set of facts valid from every possible perspective. Those are claims about the structure of reality. And increasingly, at least some parts of the disagreement are approaching experiment. Matter-wave interference has been demonstrated with larger and more complicated objects than the founders of quantum mechanics could realistically have imagined controlling. Modern experiments continue to extend coherent superpositions into regimes containing thousands of atoms. At the same time, increasingly sensitive tests place tighter constraints on objective collapse models by searching for unexplained loss of coherence, heating, radiation or motion. Simplified versions of Wigner's friend experiments have also begun moving questions about observers and quantum facts away from purely imaginary laboratories and into real optical experiments. None of these results has yet forced everyone toward one interpretation. No experiment has revealed a universally accepted mass at which quantum mechanics fails. No definitive collapse signal has appeared. No laboratory demonstration has settled whether the wavefunction is a physical object, a branching universal state, a guiding structure, or something more closely connected with information. So the embarrassment remains. Quantum mechanics can tell physicists, with astonishing precision, which outcomes are possible. It can tell them how strongly those possibilities are weighted. It can predict the statistical pattern formed by thousands or millions of measurements. And then the apparatus produces one event. One record becomes the one written in the laboratory notebook. After more than a century of quantum theory, physics still does not possess one agreed account of why that particular transition from possibility to experienced fact occurs. Perhaps the equations are incomplete. Perhaps collapse is real, perhaps nothing collapses. Perhaps one hidden configuration is actual. Perhaps facts themselves are relational, or perhaps the final resolution will require an idea that has not yet been invented. For now, the measurement problem remains what it has quietly become over the decades. Not a failure of quantum mechanics, not merely a philosophical curiosity, but an active research program built around one remarkably simple question. Quantum theory tells us what may happen, and how often. What it still does not tell us, in one universally accepted physical story, is why one of those possibilities becomes the world we actually see.